Okay, obviously ketone. What are we reacting it with? We haven't used this reagent for during this test material. Sodium borohydride, what's that a source of? H minus, okay? I don't think we've used lithium aluminum hydride before, but it's also a source of H minus. And both of these are. So that's your nucleophile. Now, sodium borohydride is a boron with 4 H's, and because that's 4 electrons, that's a minus, and you got a sodium. Aluminum is below boron on the periodic table. There's also 4 H's on it. It's also a minus charge. The counter cation happens to be lithium here. Just with this, lithium just tends to be the most common, where here sodium tends to be the most common. Otherwise, both of these metals are like, I don't like being minus H, you and your electrons take a hike. I'm going to shoot out some H minus darts. Which one of these is more reactive as an H minus? Which one is more eager to get rid of the H and but go back to neutral? Aluminum is below boron on the periodic table. Which one's more electronegative? Boron's more electronegative, means boron likes minus more. That means aluminum likes it less. So the aluminum being minus is even more bad. It's like, okay, you really got to go. Lithium aluminum hydride is a stronger hydride source. But the rationale can go back to basic ideas. It's like negativity here, okay? We'll see differences in reactivity of these. You wouldn't think much difference, but stronger hydride source. You put this in water, you got a fire. Because H minus will react with water, make hydrogen gas, and it will ignite. You can put this in water and it'll react fairly slowly. Okay? Well, lithium aluminum hydride is often abbreviated as LAH. Kind of slang, LAH. Okay, H minus source. What is the nucleophile going to do to this? Do what?
Turn the carbon into an OH.
Well, what is it going to do mechanistically? Nucleophile isocarbonyl. We've been doing that for 3 weeks now, yeah? Okay, what do you get? You get phenyl. Electrons up becomes minus. There's a methyl. What's now on this carbon? H. We're doing H minus as a nucleophile. We first used sodium borohydride in organic 1 with the oxymercuration. Okay, nucleophilic addition. Anything really new here thus far? No. Okay, what's next? Reform double bond and kick off what? Plain carbon ain't going to leave, plain H ain't going to leave, phenyl ain't going to leave. There's no leaving group. You cannot reform carbonyl. This is not an acid derivative with some type of electronegative. Game over. That's it. You cannot do an elimination. You can put a proton on, okay? Some type of H plus source can be available. We'll talk about that. This would just put the proton on, and you get this alcohol. That's it. Game over. Nucleophilic addition. Pick up proton. There's no leaving group. Aldehydes and ketones don't have a leaving group. You cannot reform the carbonyl. Okay, you see this H here? You see it right there? It's there. Unfortunately, I will see all the time where we don't recognize where their H's are. Okay. There's no H on that carbon, right? How many are on that carbon now? 1. Where did it come from? Nucleophilic addition of hydrogen. Either reagent can do this. We'll have to talk about the H plus source. Okay? Maybe I think it's shown a little bit below. We got to have an H plus source. Product down here. It's no different. That's a ketone, this is an aldehyde. This is a source of what? H minus. Only thing you can do here is add carbonyl, electrons. These electrons, nucleophilic addition to carbonyl, electrons up. Electrons up gives O minus. Now have H. We now have another H. There's actually now two H's there. And game over. You cannot reform carbonyl. What can you do here? The only thing you can do here is pick up an H plus source. I'm going to put this in quotations. It can either be acid or it might either be like water or alcohol. Protic solvent. Now what do you get? 1, 2, 3, 4. 1, 2, 3, 4. There you go. You get that alcohol. Please don't be freaked out because I drew the oxygen this way instead of up. It's a 4-carbon primary alcohol. Right? Now some books and some tutors will say, okay, reactive hydride with an aldehyde, you get a primary alcohol. Please memorize that. No, don't memorize that. Learn your mechanism and then step back and say, it is a primary alcohol. Okay? Please don't memorize outcomes. Work through the mechanism. You know what it is. I'd rather you know structure instead of some memorization of what it is. Everybody knows that's a primary alcohol. Okay? People say, well, ketone reactive hydride gives secondary alcohol. So what? That doesn't help you do anything and move on to biochem and learn how to do biochemical mechanisms. Think mechanistically. Okay, how do these first two look? It's actually easier than acid derivative chemistry because all we're doing is nucleophilic addition. We're not doing the elimination. Game over. Cannot reverse. These will not lead. We will point out when this can lead, but I say anytime you can make a pi bond reform carbonyl, but you're not going to kick off plain groups like this. Okay. Well, you should be able to do the next one. Go ahead and do the next one, number 3. Before I race, we should have answered some of these questions over here. First one's kind of review. Actually, all that's review over there. All that's review. Let's answer this one here first, then we'll go back. Somebody got the product here? Matt, you got something?
I got 2-phenylbutanol.
You even named it. Let's see, 2-phenylbutanol. Let me draw that from the name. Well, you need to clarify where the OH is on your butanol. You told me where the phenyl was, but where's the OH? Is it 2-phenyl 1-butanol or 2-phenyl?
I think it's 1-phenyl 1-butanol.
1-phenyl 1-butanol?
Yeah.
1, 2, 3, 4. So that's 1-butanol, and you want a phenyl here.
Yeah.
Okay, let's see if our mechanism gives that. What's this a source of? It's a Grignard. It's the R minus. These electrons add to carbonyl, electrons up. Electrons up, we get minus, and there's a phenyl here. And there's also an H there, but do I need to draw that in? I draw in the H's of my aldehydes. I don't draw in any H's anywhere else, but there is an H here. This is then going to need a workup to get this H on. Okay? Very often it'll be, here you would have to have H plus workup. That's how you would get the H on, and you would get that. And indeed, it would be 1-phenyl, 1-butanol. I just switched. That's the core structure, right? For 1 and 3, here's 3. Is the product R or S? Well, is it chiral? Right here, chiral. Is it R or S? Well, is anything over here optically active? Is that chiral optically active? Is that chiral optically active? No. So that can't be. So it's either R or S. If it was R, it'd be optically active. So what is it? What is that over there? It's racemic. Remember, optical activity cannot just be generated out of the blue. If you do this reaction and get all R, you get Nobel Prize. Probably super quickly, like tomorrow. Why is it racemic? Because this carbonyl, that's planar, sp2 planar. And the phenyl actually does not come right up the gut. Here's the carbonyl, okay? It's planar, trigonal planar, pretend like that's a carbonyl. Okay, going up, there's a double bond O. This reagent does not come, the Grignard does not come straight up the gut. It either comes in this way and pushes that back when it becomes tetrahedral, the oxygen, or it comes in this way and pushes it that way to the planar. Which side is it going to come in? Front or back? 50-50. That's why you get the oxygen either, the phenyl is either back or forward. I'm not going to show it, it's just racemic. Okay? Whenever you attack carbonyls, carbonyls are planar. You either attack from the front, move the carbon oxygen back. Okay? Same thing up with number 1. Number 1 was a chiral product. If you look at it, carbonyl carbon became a chiral carbon. It's going to be racemic. This product was not chiral. The carbon with the OH here is not chiral in the product, so the question is irrelevant. Okay? Let's go back up here. You have the products on your page. For number 1, what reagent would convert the product back to starting material? We got that alcohol, right? What would convert it back to the ketone? One of the big 3. That's an alcohol. Going back is an oxidation. Right? That's test 1. That's an oxidation. Thus going this way is called what? Not an oxidation, but a, yeah, that's a reduction. Very often you put H in brackets. This way you put like either O or for ox in brackets. Usually it's O, but I usually just put ox in brackets. Well, we've already said that anytime you add H's, that's a reduction, right? And going this way, we remove H's because you have to remove 2 to get that. Removing H's, that's an oxidation. Here, the carbon has 1 bond to a more electronegative atom, but now it has 2. So you can see it's been oxidized coming this way. So there's all types of ways to judge this that we've talked about before. And this is actually a redox cycle of going from your alcohols to your carbonyls. The reverse we did during test 1. Now we're doing the reduction, going the other way with that type of reaction. And if you look on the other side here, this kind of summarizes it with a biochemical process of estradiol being converted to estrone. What's the difference in the 2 molecules? right here. Here you have the secondary alcohol. Here you have the ketone. One of the big three would do this in lab. In the body, NAD+ does it. You'll learn that in biochem. That's your body's oxidizing. Your body doesn't use chromium trioxide. Okay, how would you come this way? That's a reduction. What would do that? Sodium borohydride or LAH. Because how do you do that? H- adds carbonyl, electrons up. That's how you get that H there. Then the O- picks up the proton somehow. So there's your redox cycle. By the way, your body doesn't use LAH or anything. Your body uses as a hydride source NADPH. That's your body's hydride source. We'll learn about in biochem. So that's an example of the kind of redox cycle between your ketones and aldehydes and your alcohols. And if you want to look more about this, we don't have a lot of time, but NADH and all that is kind of shown over here, so a variety of things. Even down to how cholesterol drugs act. Okay? All right. Now it's very common here in synthesis, go backwards. Let's go backwards here. The product here was this here. Let's think, what type of product here? What if we could go backwards here? You cannot, but if we could, that would help us visualize how we could put it together. What if we could make pi bond and kick off a phenyl? That would give maybe a carbonyl plus phenyl. What would the phenyl be at this point? That'd be a minus, wouldn't it? Because it took on electrons there. I kind of lost it. Okay, I'm just sort of visualizing. Yeah, it's protonated probably, but I'm not doing a strict mechanism. I'm just kind of saying, hey, I could kind of go back and see this reacting with that to give that. I'm trying to visualize how I would make that if I was asked to make that. So I can kind of come backwards. Now let's go forward. Could I get that by reacting that with this aldehyde? Sure, that's what we just showed. So in terms of, this is called sort of synthon approach or disconnection approach. Okay? Alternatively, and so I can envision making that bond right here. I cannot envision making that bond. I see no way to make that bond. Two plain carbons reacting with each other. Very difficult. Much easier here. Go back to the carbonyl here. This is really, what could supply this? Grignard. And then here, there's an H there. Yeah, there's an H there. So, here. The question is, show 3 different reactions that would give this product. Starting with carbonyl. So show a carbonyl reacting with something to give that product. And if you do this, there's actually 3 different reactions you could show. So just show one. I'm asking you to start with a carbonyl compound, right? I mean, what if we make carbonyl and kick off the methyl? Now that's not going to happen in real life, but this can allow us to go backwards and to separate things, and that would give us carbonyl here. What else is on this carbon? H. Now coming forward, what would we react that with to get this? CH3 minus. That would be in the form of maybe this. So this would be a reagent. Here would be your carbonyl. Mechanistically, if this added here, this would come up. And then we have some type of workup. So you could react benzaldehyde with methyl magnesium bromide. That would give it. There's one reaction. Somebody have another reaction that would give that, starting with a carbonyl compound. What aldehyde? That aldehyde? Plus what? Barney?
Phenol with magnesium.
Phenyl magnesium bromide, which is a source of just your phenyl anion. So you want this to add here, electrons up. Electrons up would be minus, there would be an H there, and there'd be a phenyl there. And then this will pick up a proton somehow. Is that the same thing? Yeah. It is the same thing. So there's another reaction with a carbonyl. Okay, there's one more you can do. Somebody got the third one?
One we already did.
Trey?
One we already did. LAH.
Well, tell me what would it be? You're reacting what with LAH?
The phenyl with the carbonyl.
And what's on the carbonyl?
H.
Just an H?
No, methyl, sorry.
Well, if you react this with LAH, you're going to end up with a CH2OH, and that's not that. So what do you want to react it with?
Methyl.
Well, methyl here. That with that, H minus, add here, electrons up. We get phenyl, electrons up, minus. There's a methyl, there's an H. And then this can pick up. If that picks up protons, does it give that? Yeah. There's your three different disconnects, or three different ways to make that one compound, starting with a carbonyl compound, and bringing in the other portion as a nucleophile, in the form of a Grignard for your carbanions, or LAH, or sodium borohydride if you want an H minus to be brought in. Now remember, the wonder twins, okay? In the form of a Grignard. Remember that? One of them would be in the form of water, the other would be in the form of a water bucket. And the water would go in the bucket and they would pour it on the fire. That would be 1982 again. Okay, number 4, what's the product? Okay, at this point, guys, you've never seen a reaction of an acid chloride with LAH. That's what we got here. But who cares? You've never sat down and done 567 times 39.8. But who cares? I bet you could do it. Right? The principles are all here. What are we doing first? Hydride source. Today, tomorrow, 1,000 years. Electrons up, right? What else could you do?
You could reform the pipeline.
No, I mean here at the beginning. What else could you do other than what I did? I see nothing else. There's no acidic H. That's the power of the acid chlorides. We don't have that problem. This is the only reactivity you can do. And so we get a chlorine, an H, and that's that. What do we call that? Nucleophilic addition. Okay, what do you want to do now? Why do you want to reform pi bond? We didn't reform pi bond up there. Oh, we have a leaving group now. Oh, okay. So anytime we can make pi bond and kick off a leaving group. Now we're doing acid derivative chemistry. That's an acid derivative with a leaving group. What does that give? It gives that plus Cl minus. It gives what? What did I say it gives? I said aldehyde. What is an aldehyde? Okay. Yeah. I don't know, I was just doing mechanism and that's it. But you're right, it is an aldehyde. Okay. Now what? Might be game over. But it's actually not. Because can LEH react with an aldehyde? Look back at number 2. H minus comes in again. And what does that give? I'm going to draw both H's there. O minus. Then we get some type of workup. And what's our product? Isopropyl CH2, CH2, CH2OH, CH2, CH2OH. Right? I can already anticipate the question. Go.
Can that aldehyde be isolated, or is that intermediate in bracket?
We will isolate it here. With LEH, the reaction never stops. If you can keep adding, keep adding. When we reform carbonyl, we now have an aldehyde. Aldehydes can be attacked again. You keep going. You only stop with carbonyl chemistry when we say you can. And we give a unique reagent. Otherwise, keep adding. This actually supplies 4 H minuses. We only use 2. Okay? With LEH, keep going. Mark.
So you're just going to leave that Cl minus in there?
No, you'll probably extract it, wash it with water, Cl minus go away in the
So
water.
it doesn't like attack the H again.
Attack the what?
Takes off the H.
An H.
Yeah.
There's no acidic hydrogen in the molecule. That H is not acidic. Aldehyde H is not acidic. Karen?
What's the difference between H plus workup and
And H plus what?
H plus source?
Nothing. An H plus workup would require you adding in an H plus source. It can either be a strong acid or it can be water. We'll clarify that at some point. Okay? We'll get more details at some point. With sodium borohydride, you can include a proton source in the reaction. Like do it, okay, you guys are reducing the imine in lab with sodium borohydride. It's the same mechanism, except it's an imine instead of carbonyl. Your product has an H on the nitrogen. Where did it come from? Source of what? Sodium borohydride doesn't supply H+. Because if you've got an O- and you want to put an H on it, you need an H+. O- and H- don't react to give a neutral OH. It actually comes from the 1-propanol solvent. The solvent supplies the proton. It's a proton source. So borohydride, you can do it in a proton source. LAH, you cannot have a proton source during the reaction because it will take the proton. It's more reactive. LAH, you have to, as an endpoint, throw in some acid or water. Okay? Very often on my quizzes or tests, I will say, assume appropriate workup. Basically, we can somehow get an H on there and go neutral. Okay? There's a lot of practical details in there that we just don't have time to point out right now. Okay, what if you wanted to stop here? Okay, you can't stop there with LAH, but what if you wanted to? Well, chemists developed a way to do that. If you use dibol H and do it cold, this stops at the aldehyde. Okay? It will stop at the intermediate aldehyde and will not add again. As long as you're lucky and do it right. Keep it cold. Why minus 78? Why not minus 74? Minus 80? What is this the temperature of? That's dry ice and acetone. Very common. Put dry ice and acetone, it'll get minus 78. So that's why that number is like that. Matt?
Why does it stop there?
Okay, let's look at that. What is dibol? Dibol is diisobutyl aluminum hydride. So it is an aluminum hydride with two isobutyls. Isobutyl, organic, okay, is a dibol, or dibol H. What's the difference between this and LAH? There's only one H here. LAH, I've already got it drawn. What's the difference? Which aluminum is mad? Aluminum's mad. Take a stronger hydride source. Because it's neutral, it's a weaker hydride source. You may be thinking, why does it want to get rid of an H? Well, a step that we're kind of glossing over and not mentioning is, some of these electrons down here, may first coordinate with the aluminum. Have we ever seen electrons coordinate with aluminum? Remember the Friedel-Crafts reaction? And once the electrons coordinate, then the aluminum becomes minus. Then it's like H take a height. So it requires a little activating. Okay. It's less reactive though. What else makes this less reactive? Sterics. These big groups here put these wings on here. Now this H doesn't just float out into space and then attack. The whole thing has to approach, and then the H minus is pushed in. Okay? We don't look at that in close detail. But the big isobutyls keep it from approaching as quick. You know, half the time it's like bouncing off because the wings keep hitting. Boom. You know, if I didn't have any wings, I'm just coming in. Here I come. I'm reacting. So the sterics also slow it down. Cold temperature slows it down. And if you get lucky, you can get a good yield and you can stop it here. If you use LAH, it ain't going to stop. Here I come. Does that kind of make sense? Dibol H is called a hindered hydride source. Okay? A hindered hydride source. There may be others talked about in the book. Okay, predict the product down here. 6. I'll give you a hint. Just like with LAH, with Grignards, keep adding until you can't add again. or with ethyl lithium. How we doing?
Oh.
There is some type of H+ workup required. Okay? Very often in discussions or quickly on the board, that step will be omitted. Everybody got that? It's no different than this up here. The product up there, instead of 2 ethyls, had 2 what on that carbon? 2 H's. Because hydride attacked that carbon twice. Down here, ethyl attacks it twice. And you end up with... Now some people will say that acid chlorides react with Grignards to give tertiary alcohols. So what? I know that's a tertiary alcohol mechanism. How's that look? What was the intermediate here after the first addition of the Grignard? It's actually ketone, but it doesn't stop there. Grignard adds again. You get the second ethyl on there, O minus. O minus picks up a proton. Grignard doesn't stop here. What if you want to stop there? Can you stop there? Well, you actually can. What reagent would stop there? Number 7. I don't think we've seen this organometallic. This is called an organocuprate. We'll try to look at a structure of that. What is the charge of the copper and 2 ethyls total? How'd you know that?
Plus.
Because lithium is plus? Yeah. This is a copper with 2 ethyls, and the copper is actually minus. The copper is usually plus, but it can be minus. Lithium plus. Now this copper doesn't like being minus. It'd rather be plus. We put it into this position because chemists can make molecules do things. But that copper is not happy. What would it like to do? It would like to tell this ethyl group to take a hike and take your electrons with it. So if this takes a hike, what is this a source of? It's basically R minus. Your organocuprates are sources of R minus analogous to a Grignard. Or here. But the organocuprates are just typically less reactive. Question? Valerie?
Yeah, I think it's 3 carbons on that one.
Classic rookie mistake. Thank you. Okay? Because very often when you lose something, you see, I wanted to draw a hook there, what, angle. What? So that, but really, when this comes off, it's just a straight line. 2 carbons is just a straight line. You see, I was eager to draw this here, and it made me draw 3. Yes, exactly. It's all right. It's just inherently not as reactive as Grignards. It would take an hour to explain why. But your organocuprates, when you use them with an acid chloride, or let me just show the product here. That's the product. The product is it will stop at the ketone, analogous to Dibol stopping at the aldehyde. Now, this is a great way to make ketones. Acid chlorides with organocuprates. Great way to make ketones. What other way have we seen to make ketones in this class? The only other way, we've seen Friedel-Crafts acylation, that gave ketones. The other way would be to take this with the big 3, oxidize it to the ketone. Why is this so much more of a versatile approach? Because this approach, you're able to bring in 2 big fragments and join them up. Where here, you don't change the number of carbons. You just, okay? Being able to make ketones by joining big fragments is very powerful and versatile. I don't have time to show you how to make cuprates. You're not missing out on anything. But recognize the structure of the cuprate. Okay, there's some miscellaneous things. Please do reactions on the flip side. Okay, test. We're not ready for Monday. We'll have to move the test to Wednesday. Any objections? Speak now or forever hold your peace. We have an objection. Okay, I need to pass back the quizzes. Also, let me remind you that the